Hey JEE aspirants, I am Tarush Rajput, currently pursuing BTech at IIT Kharagpur. The lecture that we are going to discuss today is only for the students that have completed their JEE main syllabus and they want to study more for JEE Advanced. So they can see this lecture and continue studying from my channel. So this is the lecture that you must study after studying kinematics for the topics of JEE Advanced Plus, like for the topics that are ahead of JEE Advanced. Like if you have completed the syllabus for JEE Advanced, you should study these topics only then. Otherwise, you should not study this topic. The topic for today is cylindrical coordinate. Cylindrical. So you must have studied rectangular coordinates, which is XY plane basically. The projectile motion that we study in like beginning of kinematics, the 2D motion, the 3D motion, the 2D motion, and the 3D motion, the XY plane. That is all the rectangular coordinates. Rectangular coordinates. Taking it further, we have studied tangential and normal coordinates, normal tangential coordinates. This is basically the circular motion. For example, we represent it by nt, the circular motion. Whenever it takes place, we say that the path traveled by a particle along is in a tangential motion, and perpendicular to the motion of the circle is the normal component, normal and tangential. And we know that in a uniform circular motion, this is zero, tangential acceleration is zero. So that is why it moves with a uniform velocity. Uniform velocity, that all we have studied before. Now taking it to another level, we have cylindrical coordinates, which is represented by r theta. It is basically the analysis of a particle, the path of a particle from a point. For example, we are considering a point at the origin, and let this be the path of a particle. This is a particle at any time t. At any time t, let this be the particle. Now we are observing the motion of the particle from this point, known as the origin. So we'll say that this is the length r and this is the angle theta. So we represent the current direction, current position of the particle as r and theta. Now, when will this be useful? When to use this usage? Use this when a motion is constrained or through a radial direction, which means it is following a path, basically a circular motion only. Radial motion. It is basically, for example, let us consider a circular motion. Here, r is constant, however, theta is variable. But we can consider it as cylindrical coordinate system also. So all the questions of uniform circular motion can be, or non-uniform circular motion can be solved by this approach as well. Or you can use this in unconstrained motion when it is observed by the measurements of a radial direction or an angular position in an unconstrained motion, where both r and theta is variable. And we'll study some examples related to this part later in this video, because this all this question all the examples of this can be solved by NT, normal tangential coordinates as well. So we'll focus more on this, and you can solve these questions with the help of cylindrical coordinates as well. So basically, what is the theory of this? So let's consider our plane, and this is the path which is traveled by a particle. Let's say particle A. Particle A. This the particle is moving in this path. The arrow is the direction of the particle. So at any time t, at any time t from the origin, we are taking the distance as r and the angle theta. So we get the cylindrical coordinates currently as r and theta. Now, one thing to make sure is that this is ER, this is E theta. What is ER and E theta? ER is a unit vector in direction of R, and E theta is a unit vector in direction of theta. Simple. So at any time t, at any time t, we would specify the location of particle in vector form as r vector at any time t is equals to the magnitude, the r vector, r multiplied by the direction, or in the multiplied by the unit vector in the direction of the radius of the like this vector, r vector. So we got the vector at the position of the particle at any time t from the origin as r multiplied by the unit vector in the direction of r. Now, to find the velocity, we just have to differentiate it. Velocity, we have to differentiate r at any time t. But it is not that simple that we have studied in rectangular xy or nt. What is the difference here? R at any time t is equals to r naught er dash. Now, let's see this example and study what is the difference. Here, see. Now, let's assume that the particle at after any time dt moves here. So, this will be the new, this will be the new r. If you notice one thing, you get that the new r, the magnitude of new r is not the same as the old r dash. So the magnitude is changing and the direction, let's see by pink, er dash and e theta dash, because it has moved by an angle d theta. So both these e theta dash, er dash will have different directions. So this is also changing. So after time dt, what we will observe is that The original r vector was in this direction. The new r vector is in this direction. Er, er dash, and the let's say another dr vector will be perpendicular to the original direction, and dr vector er cap unit vectors, and this is the angle d theta. Notice that if this is perpendicular to the original er vector, so, and we also know that the e theta was originally perpendicular to er vector. So this is the dr vector is in the direction of e theta only. Now, how would we write dr is the question. Dr vector is nothing but the magnitude, for example, wait. For example, if we have an arc of radius r and theta, we measure this as r theta. So the length of this multiplied by the angle in between. Just this logic we are going to apply here. Dr vector is equals to magnitude of er cap into d theta multiplied by the direction, because it is a vector, dr vector, so we have e theta cap, the unit vector along the direction of dr vector. What is this value? This is equals to 1 into d theta into e theta cap equal to dr vector. So dr vector is basically d theta into e theta cap. So we have this value. Now differentiating with this with respect to time, we get dr by dt is equals to d theta by dt into e theta cap. So now d theta by dt is basically omega, which we can use afterwards. This is, let's say, equation number 1. And we have to differentiate r at any time t. So to get the velocity, r at any time t is equals to magnitude of r into er cap. So dr at any time t upon dt is equals to d magnitude of r by dt er cap plus d er by dt. Okay, this is der, change in the direction of change in the magnitude. So this is der. It's not dr, der. Yes. So der cap into magnitude of r. Basically applying the product rule for differentiation, we get this. So dr, we have v velocity at any time t is equals to dr by dt into er cap plus magnitude of r vector into this equation we are applying here. So we get e theta cap d theta by dt. So basically it is dr by dt er cap plus d theta by dt into magnitude of r vector into e theta cap. So velocity is currently having two coordinates, one along r and one along theta. Along r, we can simply write dr by dt, change in magnitude and of the distance of the particle from the origin, and the theta, for the component along the theta, we can write it as r into omega, which is basically r d theta by dt. So basically this comes here and this goes here. And if we have to write velocity at any time t, the magnitude, we simply write vr square root of vr square plus v theta square. We get the velocity, the magnitude of velocity at any time t. At any time t. Now, one thing. Since we calculated that the ER and E theta is changing to ER dash, similarly, the E theta is also changing. And this is changing in an opposite sense. For example, let's take this example as well. Originally, E theta was here, let's suppose. After taking an angle of d theta, it is going here. Yes, d theta. So E theta and E theta dash. So this is the change in d E theta vector. Notice one thing, that this is perpendicular to the original E theta. Let's go back to the original figure. This is E theta. This is E theta dash. This is E theta dash. This is the change in the direction. So this and this are parallel. Let me use another color pen. This direction and this direction are parallel and opposite. See, D, E, theta and E are basically have opposite directions. So if we go back to the problem, this direction is basically E R negative in the negative direction minus E R cap. So if we have to write d e theta, again we use that approach of the length of an arc. This is r theta. Basically, we will multiply the direction, the magnitude into the d theta, and then we will multiply it by the direction minus e r cap. So we get the vector d e theta is equals to, this is 1, this is d theta, this is minus e r cap. d e theta vector is basically minus d theta e r cap. Again, differentiating with this with respect to time, we get d e theta by dt is equals to minus d theta by dt into e r cap. Why do we need this? Because for the next step, for finding acceleration, we would be needing this. Finding acceleration. How do we find acceleration? Simple, we differentiate velocity with respect to time. We know the equation of velocity at any time t right now is velocity at any time t is this. So differentiating this with respect to time, dvt by dt is equals to d2r by dt square e r cap plus dr by dt into der by dt plus dr by dt e theta cap d theta by dt plus d plus r into d2 theta by dt square e theta cap plus the last term r d theta by dt d e theta by dt. So dvt by dt is basically d2r by dt square er plus dr by dt. We have this equation from this equation number 1, der by dt. What do we have this? We have d theta by dt into a theta cap. D theta by dt into e theta cap plus dr by dt d theta by dt e theta cap plus r d2 theta by dt square e theta cap plus r d theta by dt d e theta by dt. What do we have? Minus d theta by dt into er minus d theta by dt to er cap. So we get the acceleration at any time t is equals to, let's separate the variables, the components basically, d2r by dt square minus r d theta by dt whole square into er cap plus dr by dt into d theta by dt plus multiplies 2 because we have two terms plus r d2 theta by dt square. This we have e theta cap. So we can basically represent the acceleration at any time t as a r vector and a theta vector. A r vector will basically be this d2r by dt square minus r d theta by dt square, and e theta, its acceleration along theta, we can write it as 2 dr by dt d theta by dt plus r d2 theta by dt square. And again, magnitude of acceleration, we can find it out by ar square and the root of ar square plus a theta square. So this is the entire theory for cylindrical coordinates. Nothing is required except for that. Now we'll be moving on to questions related to this topic. Now this is the first question. We have given an equation of theta as 0.2 t plus 0.02 into t cube and r as 0.2 plus 0.04 t square. Now let's read the question. Rotation of the radially slotted arm is governed by this equation where theta is in radian and t in second. Simultaneously, the power screw in the arm engages the slider B and it controls the distance from O. So the distance is also changing and theta is also changing with any time t. So where r is in meter and t is in second. Calculate the magnitude of velocity and acceleration. Simple. So we have r. So we can do it. We can find r at any time t as r and er. Let's take this example only. Hmm, yes. So this is r at any time t, and this is theta. So let's say that uh, this is er, basically a unit vector along direction of the r from which we are measuring it, and this is e theta perpendicular to er. Simple. E theta cap, er cap. So r at any time t is this drt by dt is dr by dt into er plus r der by dt, and this is v at any time t is basically dr by dt er cap plus r der by dt. So after getting velocity at any time t, we differentiate it for acceleration d2r by dt square er cap plus dr by dt der by dt plus dr by dt d theta by dt into e theta cap plus r d2 theta by dt square into e theta cap plus r d theta by dt into de theta by dt. So basically we get d2r by dt square into er cap plus dr by dt. Der by dt we have d theta by dt into e theta cap plus dr by dt, dr by dt, d theta by dt, e theta cap plus r d2 theta by dt square e theta cap plus r d theta by dt into d theta by dt. We have d theta by dt, so squared, minus er cap. Arranging it in component form, we get d2r by dt square minus r d theta by dt whole square er cap plus 2 dr by dt d theta by dt plus r d2 theta by dt square E theta cap. This is A at any time t. So basically, you don't have to remember all the equations that we have discussed in theory. You can just derive it. You will just take 5 minutes for the derivation if you know the concept. So we have the equation of theta and r. We just have to put the values now. Theta d theta by dt. We have 0.2 plus 0.06 t square, and d2 theta by dt square we have 0.12 t. Dr by dt we have 0.08 t. d2r by dt square we have 0.08. The question is asking us to find the magnitudes of velocity and acceleration at time t equal to 3 seconds. So at t equal to 3, d theta by dt is 0.2 plus 0.06 into 9. So basically 0.2 plus 0.54, 0.74, and d2 theta by dt we get 0.36. dr by dt 0.24, d2r by dt square 0.08. So we have the equation of v at any time t. V at any time t is dr. We can write it as dr by dt, and v theta we can write r d theta by dt. So what do we get here? Dr by dt is 0.24. Vr v theta r d theta by dt. So 0.74 into r. So we also need to find r at 3. 0.2 plus 0.36, 0.56. So into 0.56. So we get velocity is equals to the magnitude as Vr square plus V theta square. So on calculating, you will get the magnitude of velocity as a 0.479. And now the task that I'm giving you is to find the magnitude of acceleration. That will come out as 0.601 meter per second square. You can use calculator for now, but try to do it on yourself only. That will speed up your calculations. That's that's it for the picture.